Solving exponential equations. In this first part, I'm going to solve exponential equations where the expression on each side has a common base. For example, 5 to the x equals 1 over 125. So problems like this, I can do by hand and get an exact answer without a calculator. In the second part of the video, we're going to do problems that you can get exact answers that have logarithms in it, but we would need a calculator to get the decimal approximation for. And I say that because we could also do the same thing in this first part. I just don't want to because I can solve these easily by hand. So what do I mean by expressions with a common base? The left side of the equation has a base of 5, of course. I have 5 to the x. And the other side, if I think about it, is also 5 to some power. Well, I know that 5 squared is 25. 5 cubed is 125. So 1 over 125 is 5 to the negative 3. And when we have an expression with a common base in a form like this, I don't divide by 5, I don't do a lot of fancy work. I can simply ignore the 5s because it should be obvious to us that if 5 to the x equals 5 to the negative 3, then x must equal negative 3. Let's do a couple more examples like this, perhaps a little bit more complicated in appearance. Let's try 4 to the 2x equals 2 to the 3x plus 1. Now, the expression on the left is base 4. The expression on the right is base 2. But I also know that 4 is 2 squared. So if I rewrite the left side as 2 squared to the 2x equals 2 to the 3x plus 1, and then use my properties of exponents on the left side, when we have a power to a power, we multiply the powers, giving us 2 to the 4x equals 2 to the 3x plus 1. Notice that I have reduced the expression down so that the expression on the left is a base 2 and the expression on the right is also a base 2. So if 2 to the 4x equals 2 to the 3x plus 1, well then the powers must be equal. That is 4x must equal 3x plus 1. And then solving, we get x equals 1. Let's try one more of these. Let's do 9 to the x equals 81 to the 1 minus x. Now they both have base 9. That is, the left side is base 9 already, but 81 is 9 squared. So I could rewrite 81 as 9 squared and then to the 1 minus x. Rewriting again, I'm going to leave the left side, 9 to the x, but on the right side I will use the property of exponents where power to a power, we multiply the powers, giving us 9 to the 2 times 1 minus x, or to the 2 minus 2x. Now that I have the same base on both sides, I can ignore the base and set the exponents equal to each other, giving us x equals 2 minus 2x. And then solving, we get 3x equals 2, or x equals 2/3. Let's look at the other type. I'm just calling this type 2. It's not something standard, just what I'm calling it to organize things. What if we have expressions that do not have a common base? For example, 4 to the x equals 21. Now, I could rewrite 4 as 2 squared, but there's no way to get 21 down to base 2 and at least not have nice numbers for us. So instead, when we do this, we can take the log of both sides. And you can really take the log of whatever base you want. Since our calculator uses base 10 or base e, I usually do just plain old log or sometimes natural log, depending on the circumstance. But whatever I do to one side, I can do to the other side, like that. What is the reason for this? And let me put this in parentheses to remind me that there are implied parentheses at least there. When I have the log of something to a power, we can rewrite this one by bringing the power down in front, giving me x times the log of 4 equals the log of 21. Now the log of 4 is one single number. It's not log times 4. It's some decimal. If I remember correctly, it's about 0.602 when it's base 10. And then log of 21 is one number, some decimal. I have no idea what it equals, but I could put into a calculator and get in a good approximation. But the point is, I can now solve for x by dividing both sides by log of 4. Now, this is an exact answer. If I wanted a decimal, use a calculator. Quick note, this does not equal log of 21 minus log of 4. Very common mistake. It does not equal that, right? When I have a subtraction of logs, I can put that together in one expression inside the argument as a division. Okay, so be careful. It does not equal that. This is my final answer if I want an exact expression. Let's do a more complicated looking problem. Let's do 5 to the x equals 3 to the 2x minus 1. They do not have a common base, so instead I will take the log of both sides. So log of 5 to the x equals log of 3 to the 2x minus 1. Properties of the logarithm says we can bring the power down in front, so I get x times the log of 5 equals, be careful in this one, 2x minus 1 times the log of 3. Now I intentionally wrote this incorrectly because when I bring the power down in front, I'm multiplying that entire thing, parentheses belong there, times a log of 3. Again, log of 5 is some decimal. It's one inseparable number. Same for log of 3. Our goal is to isolate the x. So I will do some algebra. And on the right side, I will distribute because I can. I'm hoping something like this helps. Of course, I know it will, but if you're unsure, do algebra that you can do that's correct and see where it leads you. So I will distribute the log 3, giving me 2x times log 3 minus 1 times log 3. And then I want all the x's on one side and all the non-x's on the other, if possible. So I will have 2x log 3 minus x log 5 equals the log of 3. So all the x's on one side, or all the expressions with an x on one side, and all without on the other. Because I can now factor out an x from the right side of the equation. So I get x times 2 log 3 minus log 5 equals log 3 over here on the left. And then I can divide both sides by this long expression here, giving me x equals log 3 over 2 log 3 minus log 5. Now, this left side of the equation can be rewritten in a bunch of different ways, especially considering the bottom part. For example, I could rewrite this as log 3 over log 9, right? 2 log 3 becomes log of 3 squared minus log 5. And I could go one more step if I wanted to, equals log of 3 over log of 9/5. And I could actually go another step, but the point is they're different answers that are mathematically equivalent to each other. And depending on how your professor or the software that you might use asks for it, just kind of put it in that form. Let's try one last problem. It's about as complicated as a problem as I would ever ask, at least of my own students. Let's do 4 to the 2x plus 2 equals 5 to the x plus 3. I don't have a common base on both sides, so I'm going to take the log of both sides. And I'm going to skip this step. That is, I'll take the log of both sides. I already know what will happen. I will bring that power down and multiply it. So I get 2x plus 2 log 4 equals log of the other side, bring the power down, x plus 3 times the log of 5. Again, log 4 and log 5 is some inseparable number. It's a long decimal. Our goal is to isolate the x, so I will distribute. It's pretty common in problems like this. I will distribute the log 4 on the left side, giving me 2x log 4 plus 2 log 4, which you could write as log 16 if you want. I will leave it as is. On the right side, I will distribute the log 5, giving me x log 5 plus 3 log 5. Perfectly fine answer. I now need all x's on one side, that is all expressions with an x. So I will get my x's on the left side this time. So I will have 2x log 4 minus x log 5. And then all expressions without an x on the right side. So I'll do 3 log 5 minus 2 log 4. Can rewrite that if I want to. I'm just going to leave it. I'm now going to factor out an x on the left. So I have x times 2 log 4 minus log 5 equals, and the right side can stay if you wanted to, 3 log 5 minus 2 log 4. And final step, divide by this expression to isolate the x, giving us x equals 3 log 5 minus 2 log 4 all over 2 log 4 minus the log of 5. And that will be our final answer.